it's my great pleasure, it's our great pleasure to present our next speaker for today's seminar. It's the second seminar for this year, Professor Szilard Revesz from Hungarian Academy of Sciences, if I'm right. And thank you for agreeing to deliver a lecture at our seminar. And thanks, and please go ahead.
Yes, thank you very much for the invitation to this prestigious seminar. Today I will talk about a topic which is mostly lying in the constructive theory of functions, but as you will see, it has connections to various other areas in analysis. What I will present will be mostly joint work with Bálint Farkas and Béla Nagy. Let me show you a list of papers what we have worked on in the last, say, decade. There are 6 papers we published on this topic, related to this topic, and I try to give a summary of the main findings. Also, there is a recent paper, a preprint of Tatyana Nikiforova, which I will mention. She continued this line of investigation towards the case of the real line, an infinite interval. So actually, the topic can be started from various starting points. One possible starting point is Boyanov's variant of the classical Chebyshev problem. So it's an approximation theory problem. Actually, Boyanov started with a higher order Hermite-Feyer interpolation and tried to optimize certain Hermite-Feyer operators. And so he arrived at this extremal problem. Given an interval, and we consider polynomials, monic polynomials, so with leading coefficient 1, which have prescribed nodes of prescribed multiplicities for the roots, nu1, nu2, nu_n. So say if all are 2, that's the case of which is connected to the ordinary degree 2 Hermite-Feyer interpolation. We prescribe that all roots are double roots. But general, any system of multiplicities can be allowed. And then we consider the polynomials, which are products of these root factors, so monic polynomials, and would like to minimize their Chebyshev norm, their supremum norm on the interval by choosing the roots, the nodes x1, x2, xn, the optimal way. Now Boyanov's theorem says that there is an extremal root system or node system. They are strictly different and different from the endpoints. And the extremal polynomial is characterized by the equioscillation property that there are n+1 points, including the 2 endpoints. So n-1 inside and the 2 endpoints, where this polynomial capital T attains its norm, its Chebyshev norm. So this contains the classical Chebyshev problem when all the new j's are 1, but it's a bit different because here the occurring polynomials do not form a vector space. If you consider linear combinations of polynomials which have multiple zeros, then you can easily achieve that the linear combination does not have multiple zeros. And in fact, the linear span is a larger polynomial space. So also this prescribed multiplicity special polynomials do not form a Chebyshev Haar system, not of the order n. Also here, if the news are not all equal, then there is the problem of the order, so you can consider the problem without fixing the order or assuming that the very first root has to have multiplicity nu1 and the next one, multiplicity need to, and so on. So the global version can as well considered, and there is the harder version with given ordering. The standard reformulation is taking logarithms. Standard because this is the approach what potential theory uses. Since from the 80s, logarithmic potential theory became a standard tool in approximation theory, and actually this was the best technique to give marvelous results. So I don't claim that it is new, but anyway, you can see that the product representation of the polynomial then transforms to a sum. So Boyanov's extrema problem can be reworded as minimizing the supremum of this sum function, minimizing the norm of this. And not exactly the norm, because negative values are not interested in the supremum of this sum. One can also consider the weighted case. When there is a weight and the weighted norm is considered, which is then can be written equivalently with two-sided estimates. And actually, one can pose two-sided conditions even when the two conditions, the lower and upper estimations, are different, not the same function. When all the nu are 1, these things are well known. The extrema polynomials will equi-oscillate between these bounds. So these extrema polynomials are called snake polynomials in the literature. So you see here just a picture. The upper bound is the blue one, the lower bound is the green one, and the extrema polynomial equi-oscillates. So the general weighted minimization problem is that try to minimize this W norm. Here in our lecture, we cannot deal with asymmetric weights. Also, for the time being, we fix the ordering of the nodes. So we will say that the nodes are in the simplex, where they are ordered according to the prefixed sequence of multiplicities. The weight has to be non-negative and bounded and should not be identically 0, of course. Then we can take again logarithms, and this is the form we get, very similar to the previous one, only the logarithm of the absolute value of the weight appears. And more generally, we can take just this expression, so fxt, which we will call after Fenton the sum of translates function, has the form that there is JT, a field, an external field, and the sum of translates of some kernel functions. So one goal is to keep the external field or the weight as general as we can. For instance, we want that W could be the characteristic function of some set, say a union of K intervals, because that has applications for us. So what we will assume that J is bounded from above, and it is not minus infinity, at least on n+1 points. We will call this condition non-degeneracy condition, and we will write that J is not identically minus infinity. It means that it's not minus infinity, at least on n+1 points. This is an absolutely minimal condition. One can check that this is equivalent to assume that whatever node systems we take, the sum of translates function will not be identically minus infinity. Of course, if it can be identically minus infinity, then the minimization problem is just trivial and it's minus infinity and there is nothing to do with it. Also, we will allow totally different kernels, Ki. Now, okay, so let me give more precise definitions. We will call a function K a kernel function if it is concave and two intervals and -1, 0 and then 0, 1. So it doesn't satisfy this condition at point 0, but as a second condition, at least the limit from the left and from the right at 0 has to be equal. Of course, this has an extended continuous extension because the limits exist at the endpoints and at 0. So we can as well consider K to be a function from the closed -1, 1 to the extended real line, where with the extended real line, we mean that we extend it by -infinity. Because of concavity, it cannot be +infinity. Now, okay, another condition that we frequently discuss or use is singularity, that the limit at 0 is -infinity. We will say that K is a strictly concave kernel if it is strictly concave under concavity intervals, and we will say that it's monotone. Now it is a bit tricky if it is decreasing on -1, 0 and increasing on 0, 1. So monotone, but in the different sense on these two intervals. And then also the limits at -1 and +1 should be finite. Fenton used another condition, the cusp condition. Basically, you can say that from the left, when points tend to 0, the derivative or the slope of the tangents has to tend to -infinity, and similarly from the right to +infinity. But we formulated it with slopes of the chords in order to avoid differentiability discussions, which points it is differentiable and so on. It's more general putting it this way. Of course, the singularity condition implies by concavity this infinity prime condition, the cusp condition. Okay, two examples. Left is the logarithmic kernel. This is singular. Right is the square root kernel. This is non-singular, but satisfies the cusp condition. So again, the simplex is the ordered set of nodes. The sum of translates function is this sum. We have already seen it. And non-degeneracy of the field is equivalent to saying that Fy is not identically -infinity. So then we can introduce notations for the intervals between the nodes. So Ij denotes the j's such interval, and Mj for the supremum of the sum of translates function on that particular subinterval Ij. So we have n+1 such Mj, and the maximum of them is denoted by M overline and the minimum of them by M underline. So actually, M overline is just the total supremum on 0, 1 on the function f. So the goal is the minimax problem. We are trying to minimize M overline on the simplex. But dually also the maximum problem can be posed. Try to maximize the minimum of these Mj. Also, we want to characterize the solution node systems, if any, and describe them, or approximate the external values. So an illustration is like that. Here at the nodes, we have the cusps, and in between here we had just it without weight, so an external field identically 0. So here F is concave between the nodes, and so it's easy to see the maximums, and we are dealing with these 4 maximums now. And here is a more interesting case when the weight is the characteristic function of a set. This set is the union of 2 intervals. Outside these intervals, the weight is 0, so j becomes -infinity, and it kills the sum of translates function. It will be -infinity there, so all these maximum considerations can be restricted to the rest. And this is what we want to discuss. Okay, so let me recall the theorem of Fenton. He says that let also the field be concave and the kernel K be monotone, strictly concave, even twice continuously differentiable, and the second derivative is strictly negative, and satisfied the cusp condition. Then the sum of translates function in this special case when the kernels are all equal. We have just the same K for all terms. There exists an extremal node system W in the open simplex. So it's in the open simplex, the nodes are different. So we denote the extremal value, the minimax value, by capital M, and it is attained by this system. And then for this system, the sum of translates function equi-oscillates on the intervals I, j. That is, all these interval maxima are equal. And W is the unique equi-oscillation node system, and it is also the solution and the only solution for the maximum problem. So lowercase ms also equals to this common value of the mn for the node system W. So what does this mean? One immediate consequence, just presenting it from another point of view, is that for any node system X, the extremal value, capital M, is estimated by both sides by the minimum and maximum of the MJs belonging to that arbitrary node system X. So the minimum of the MJ cannot be larger, and the maximum of the MJ is, of course, at least as large as that one. Sorry, I have to switch off the phone. So here I come to the point that you asked before the lecture, that Fenton's original goal was to prove a conjecture of Bari. Actually, I didn't give the reference, but he presented his solution in 1981 in a paper in the Journal of the Australian Math Society. And this paper in 2000 only distilled the essence of the proof as this separate key lemma or auxiliary theorem, what I presented before. But even before his 81 paper, actually the conjecture of Bari was solved by Goldberg. Now, anyway, Fenton's theorem immediately implies the solution to the Chebyshev problem, this classical problem, but not of the Boyanov problem. Why? Because, as we have seen here, Fenton assumed that all kernels are exactly the same. And also, it gives the well-known information that for arbitrary systems, the MJX approximate from both sides the external value. So here is a picture. In red, you see the Chebyshev polynomials, and in blue, some other polynomials, the absolute value of them. And as you see, the second and the fourth maxima is below the extremal value, and the first, third, and fifth are above the extremal value provided by the Chebyshev polynomial. Now, one more possible starting point, actually this was our starting point with Béla and Valiant, was a problem on the torus originating from the PhD thesis of Gergely Ambrus, who wrote his PhD in London under the guidance of Kiesball. So this is a simple looking extremal problem. Even any complex numbers of modulus 1, z1, zn, try to find another complex number z, also of absolute value 1, so that this sum of 1 over z minus zj in modulus squared would be as small as possible. And they proved that this is possible with n squared over 4. And actually, n squared over 4 is sharp. One can easily check that with roots of unity, we cannot get smaller value. And actually, this is the only system where we get n squared over 4 only. For other systems, some smaller value is also possible. So this seems to be a geometry problem, or anyway, a simple extremal problem. Let us see what is the connection to our setup. So this is, first of all, is a maximum theorem. So we look for the maximum in Zj of the minimum in Z of this sum. And the statement is that this maximum value is n squared over 4. Now, the distance of 2 points Z and W on the unit circle can be expressed with the sign, and taking kt to be minus 1 over 4 sine squared t over 2, the problem can be rewritten as looking for the minimum in t of the maximum of the sum kt minus tj. So the maximum was changed to minimax by choosing the negative sign for the k, and otherwise the reformulation is clear. So it is again a Fenton type setup here. So apart from solving the case with this 1 over 4 sine squared kernel, Ambrus and Ball formulated a conjecture that in fact k could be any concave kernel function. This same result should hold. And this was proved by Hardin, Kendall, and Saff. And also they proved that if k is strictly concave, then such configurations are the only ones achieving this inequality. Here we don't have unicity because any rotated system is equidistant too, and this value is the same. But we can step back by 1 in dimension, fixing one node at 0, and then there is unicity in this problem. So here we are interested in different kernels, and for different kernels, of course, we cannot expect that the extremal configuration will be equidistant, but it can still equioscillate. So we say that the node system equioscillates if all mjy are equal. That is the difference of the consecutive node, maxima are at 0. So we can introduce the vector function, which gives us to any node system the n+1 interval maxima, and the difference function, which gives the n differences of the consecutive maxima. So the difference function is somehow more appropriate here because we have n nodes moving, so dimensionality suggests that the properties are encoded in the function phi. So a node system is thus equi-oscillating if the difference function gives 0, the 0 vector. Another notation or another terminology that we say that a node system X majorizes another node system if all the corresponding MIX are at least as large as MIY. So this two-sided approximation of the equi-oscillating system means that no X would majorize the minimax node system. Okay, so the natural question is that how many points are mapped to 0? How many equi-oscillation points are there? Before we have seen that Fenton proved unicity of the equi-oscillating system in his setup, but actually unicity holds not only for the equi-oscillating node system. Here is a result, what we found for the torus case, homomorphism theorem. Let the kernels Kj be twice continuously differentiable, strictly concave in the sense that the second derivative is less than 0, and singular. Singularity is important. Consider the sum of translates functions. Then this difference mapping is a homomorphism from the simplex to Rn. So it's continuous and 1 to 1. Our inspiration was gained from the solution of the optimal Lagrange interpolation problem. There is such a phenomenon also. So we proved this homomorphism in steps. Local homomorphism is equivalent to the non-vanishing of the Jacobian. One has to prove properness of the mapping, and then general topology gives that it is a global homomorphism. Now, what about the minimax problem on the torus? Here is a result. Now we had to suppose that the K's are strictly concave and either all satisfy the cusp condition or all belong to C1. And we could solve the global problem. So without specifying the ordering, there is a global minimax node system W in the S power of the torus, which attains the minimax value. And it has the following properties. It is an equi-oscillation point. It is in some simplex, open simplex. So for that ordering, all the nodes are different with strict inequalities between them. And it also has the sandwich property as before. Actually, surprisingly, the result holds only in this global version. In fixed simplexes, one can construct counterexamples where the extrema point is on the boundary of the simplex, the minimax point, and it is not an equi-oscillation point. So here, indeed, it is shown that with different kernels, the situation is more tricky. What were the key ingredients? Just one more remark. As a corollary, the trigonometric version of the Boyanov theorem follows, even if without weights. Main ingredients, one has to prove some regularity, continuity, and more for the functions mj. It is not trivial. Some perturbation lemmas were obtained, and then the homeomorphism theorem under suitable assumptions. And then from the homeomorphism theorem, for the homeomorphism theorem, we had to have C2 conditions and other conditions. So for the general case, we had to apply a limiting argument. But because of this limiting argument, sometimes the unicity could not be proved. Now a remark here that for logarithmic potential theory or the strong polarization problem, singularity is a natural condition. So we can easily assume that. But Fenton's original theorem extends to non-singular kernels, where the homeomorphism theorem necessarily fails. Necessarily because if the kernels are bounded, then you cannot expect the sum of translates function and the maximum to go unbounded and to cover all the Rn. In the non-singular case, however, we still could prove all these statements, continuity, existence of some equi-oscillating node system, and so on. And for that, the proofs had to be reworked. Now, let me go back to the interval case, the Boyanov setup. We could obtain more general results, stronger results in this case. So I tried to present them in the rest of the lecture. So we wanted to allow general weights, also including the case when there are only n+1 points where the weight is not 0. If we do that, then we can actually get interpolation type results. Also, we want to cover the case of Chebyshev polynomials and Chebyshev constants for the union of k disjoint closed intervals. For the kernels, we also strive for generality. And also, we would like to get back the results of the periodic case, even with weights. So one goal is weighted trigonometric Boyanov-Chebyshev theorem. And also, we would like to discuss the majorization issue, not only for the extremal node system, between the extremal node system and others, but in general between arbitrary node systems. Here is an easy proposition. If all the kernels are arbitrary, but the field function is continuous, then of course the sum of translates function is extended continuous too. And also it's easy to see that the functions mj, the interval maxima functions, are continuous in the extended sense, allowing -infinity, extended continuous too. Also their maximum, the m over line, is then classically continuous, real value continuous, because the maximum can never be -infinity. In this case, when J is also continuous, one can get this easily by the well-known principle of continuity of the partial maxima function. So we consider maximum in one variable, and then in the other variable, this obtained maximum function will be continuous. Actually, for that, it's enough if J is upper semi-continuous, which is an important case for our study. But what happens if J is not assumed to be upper semi-continuous? And here is the first real surprise what we encountered in this thing. Here it is. If we have singular kernels, so K1, Kn singular, then for arbitrary field function, recall that the only condition is that it should not be degenerate. It should be not minus infinity at least n+1 points. So it doesn't need to be measurable, nothing. Arbitrary field function. So if the kernels are singular and J is an arbitrary field function, then still the MJ are continuous. Moreover, they are locally Lipschitz continuous wherever finite. So where the MJ are finite, here on the right-hand side, you see the niveau set. MJ is larger than minus infinity. So intersecting all these niveau sets, we get the set of regularity. I denoted it by capital Y. So Y is the regular set. And we say that the node system is regular if it belongs to this set. It means that all the MJ are finite. And if Y is such a node, then MJ is Lipschitz continuous at this point MJ. Lipschitz continuity is very important for us because it entails almost everywhere differentiability. Now, okay, here is an example. J is just a characteristic function of an interval, and K is square root of absolute value of T. Here is the calculation for the interval maxima, but it is simpler to look at this graph. This is the difference function. Now n equals 1, and we see that phi, and therefore also the MJ, could not be continuous because there is a discontinuity of phi. Also, the function phi, of course, is no longer reactive to R. So what we claimed in case of singular functions in the homeomorphism theorem cannot go over for non-singular kernels, not even continuity of the MJ. Okay, so we had monotonicity conditions before. Now, here is a weakening of the monotonicity condition. We don't assume that K prime T for T in 0, 1 is non-negative, and in -1, 0, non-positive, but only that the difference of the two will be non-negative or larger equal than C for a parameter C. So this periodized monotonicity condition means that K is the sum of a periodic function and a strictly monotone function with derivative at least C. So here is a picture. The light blue is the added monotone function. So what we try to with this condition is to have a common generalization of the monotonicity condition on the one hand and the periodicity condition on the other hand. So how far the homeomorphism theorem extends? Of course, the kernels need to be singular. And we could use the following theorem, which provides local homeomorphisms, local Lipschitz homeomorphism, even in non-differentiable cases. This is a famous theorem of Clark in real analysis. I don't have time to go into details what the Clark derivative means, but anyway, this is a version of the inverse function theorem, which works for not necessarily differentiable functions, but Lipschitz functions under a suitable condition. So of course, that's the key to prove that full rank of the Clark derivative. But we could prove this, and this led to proving that phi is a local homeomorphism. And the same way as before, to extend local to global, we needed two things: that phi is proper, that is a standard fact, and that phi is connected. So the set of regular node systems is connected. That's again kind of a miracle. But to apply the general topology to the local homeomorphism becoming global, this is a necessary thing. Now, okay, so let K satisfy the periodized monotonicity condition with some C and take an arbitrary field, then we have this difference function, and it is a Lipschitz homeomorphism between the regular nodes and Rn. And it extends to PM0 if J satisfies some mild conditions. So we succeeded in extending to the periodic case with almost arbitrary field functions. Now for further minimax results, we have to apply some restrictions. So we will now restrict to kernels which are constant multiples of the base kernel, like in the Boyanov case. Sometimes we assume that J is upper semi-continuous. And we use monotonicity conditions. Here is a surprising perturbation lemma, perturbation type result. So suppose we have a node system W, and we partition the index set 0, 1, n to two index sets. The only condition is that none of them could be empty, and therefore none of them could be the whole. So some of the indices belong to I, and some of the indices belong to J. Then we can perturb the node system W such that this closed by new node system W prime satisfies that the intervals for W prime and also the functions, the sum of translates functions, and also the interval maximum are all decreased for indices in I and all increased for indices in J. So it's a very precise perturbation type result. So once we have some perturbation lemma, how do we obtain minimax and equi-oscillation theorems? So the idea is clear. For any node system, we try to improve on the M over line X, the maxima. And how to do that? If not all the NJX are equal, so if it is not an equi-oscillating system, then some of them is smaller than the maximum. So we can apply a perturbation which does not bother with that one, but perturb all the others to a smaller value. And therefore, the maximum of these MJ could be lowered. So this says that unless we have an equi-oscillating node system, there has to be an improvement. There could be a better system, better node system. So here is just a picture. If you start out from the green one, then with a perturbation, you can decrease the maximum. Or this is another example. Where the blue system is perturbed to the orange. Here the last maximum was smaller for the blue system, and so we don't mind if the orange new system has larger maximum. So an external node system must equi-oscillate, that's the idea. So here is the minimax theorem. Let K be singular, monotone, J upper semi-continuous but otherwise arbitrary. Then the minimax and maximum values are equal, and there exists some node system which is extremal. Of course, there is also that is also regular. It is an equi-oscillating point, and it attains the simplex maximum and simplex minimax. So also the sandwich property holds, and the equi-oscillation value is unique. If K is strictly monotone, or if it satisfies PMC, then this extremal system is unique. So from this, with specializing, we get back Boyanov's result. We can also get Chebyshev polynomials and Chebyshev constants for suitable sets E, and we obtain these results with weights too. And here is another result what we obtained, that if K is singular, strictly concave, strictly monotone, and J an arbitrary field function, then for any two regular nodes, X and Y, there can be no majorization. All mjx less or equal than mjy can only hold if X equals Y. So this means that in the Chebyshev problem, any two node systems, any two root systems have the property that some of the maximums are smaller and some of the maximums are larger than the corresponding one of the other system. This was known for the extremal, for comparison with the extremal value, but not between any two node systems. At least until now, we didn't encounter any such reference. So here is a picture. You see the blue and the green arbitrary polynomials, okay, absolute values of those polynomials. And you see that some of the green maxima are larger and some of the blue maxima are larger than the other one. We conjecture that this intertwining property holds for arbitrary, not necessarily non-singular, strictly concave and strictly monotone kernels, but that we could prove only for n equals 1, 2, 3. So when we don't have the homeomorphism theorem, then this is a more difficult question. This is a stronger thing, this intertwining result, than unicity of the equi-oscillating node system that follows immediately from it. So, okay, so I presented this conjecture. Also, I have to say that monotonicity is probably necessary for this. A final discussion about the Fenton result. I mentioned that Fenton's result assumed only cusp condition. We usually use the singularity. But actually, we could prove, at least in this case of kernels which are constant multiples of each other, the corresponding minimax result and the sandwich property and equi-oscillation property. So I don't go into the proof now, because time is up. So let me summarize what was presented. So taking absolute values and then logarithms of polynomials transform classical problems of approximation theory to minimax problems and sum of translates functions. So the most essential property is that after taking logarithm, these kernels, these factors be concave, so log concavity of the factors of the polynomials. And for the weight, very general conditions suffice. We cannot handle asymmetric bounds, but the signs can be retrieved usually. So taking absolute values is not an essential restriction of the method. And very general findings could be proved: unicity, Lipschitz homeomorphism, and intertwining. So thank you for your attention. I think I should stop here.
Well, thank you very much for a very nice presentation, Professor Revesz, and we have time for questions, if any. So if there are questions, you can just raise hands. I don't see questions, but meanwhile, maybe I ask some small question. You spoke about notion of monotonicity, right? Periodized monotonicity.
Yes, yes.
It's for the first time I saw this notion. So usually when I want to generalize a condition on monotonicity, I use, for instance, almost increasing or almost decreasing, something like this. But this notion I see for the first time. Can you have some examples for a function that satisfies this? Or maybe connection to...
Oh, well, the reason why we came to this is that we wanted to get a result on the interval which also contains the results for the periodic case. So generalized periodicity and monotonicity. Now let me go back to the, I will find it in a minute. So what was the periodicity, what was the monotonicity condition? The monotonicity condition was a bit tricky one. That's why it's a bit different and the generalizations are a bit different. We said that a kernel is monotone if it is decreasing on -1, 0 and increasing on 0, 1. So here is the example. These kernels I called monotone. Okay? So,
and you need to have a cusp also, right? So you don't consider...
Yes, yes. So in this setup, it's natural that in the left it is decreasing and in the right it is increasing. But it is not the classical monotonicity when it is the same way monotonic. And on the other hand, if you want a kernel which is which gives back the periodic case, then you have to have the kernel periodic. So like the absolute value of the sign, okay? Just two identical bumps, okay? But how to get a general condition which generalizes this monotonicity and periodicity? Actually, if a function is monotonic in this sense and periodic, then it has to be a constant. Okay. You see, because if you transfer the monotonically increasing part, if you translate it by 1, then you get into the monotonically decreasing part. So periodicity means that it is both monotonically increasing and decreasing, so constant. So it is trivial. So you don't get any general result.
Okay, I see.
And so this is how it came about, and it was very, how to say, tricky to get into this.
Okay, now I understand. Yes, thank you. Well, we have a question from Elena Berdeshova. Please, can you?
Yes, please.
Go ahead, please.
Thank you very much. Best regards from Cape Town. I have the following question. It's not the first talk of Szilard I hear about this topic. How do you imagine the future work, the future development in this type of questions, in this problem? Thank you.
Yeah, well, I didn't have time to list applications. There are several applications, and there are several open questions. I can send you the file also. I send the file to the organizers, so you can see several open questions in this regard. I mentioned too about the homeomorphism theorem. So even if there is no global surjectivity, but global injectivity can be conjectured. And also this intertwining property would be interesting to get. And there are many, many directions. So the conditions under what our theorems work are quite general, but you can look for more general conditions. And these can have applications, I think. One direction is study of infinite intervals. I wanted to mention Tatyana Nikiforova's work. She could transfer the infinite to the infinite interval our results. This is an absolutely non-trivial extension of the method. So I think that there are many open questions, and already Fenton presented this because this is quite a general goal to minimize some maximum type single minimax questions. So if we can describe it in various contexts, in different generalized situations, then we can get good applications. So I think that there is continuation of this research in various directions.
May I ask a very general, maybe a very naive question? Can you apply it to solution of integral equations somehow, or approximate solution, this method?
No, the question is a very good question. Actually, it gives me an opportunity to explain in what extent we deviate from classical potential theory. So basically, the sum of translate function, I explained that taking logarithms is the standard thing in logarithmic potential theory. So this sum of translate function is like integrating the logarithmic kernel against a discrete measure. You have measure nu I at the point xi and integrate this measure against the logarithmic kernel. Now, logarithmic potential theory is so powerful in approximation theory because it handles the limiting case. What happens when n tends to infinity? What you can expect, how large this supremum will be, and so on. So it can transform this to energy questions and so on and so on. And your question is kind of similar. What we can study very well is the discrete case, discrete measures, integral transforms of general kernels against discrete measures. But the limiting case is a bit less clear. So there is hope that if you can obtain very precise results for the discrete case, then you can derive something for the limiting case. But it's not obvious. So classical logarithmic potential theory and approximation theory is better in these limiting things, but sometimes doesn't give so precise results for the discrete case. And our study gives more precise results in the discrete case. So this is the connection.
Okay, very, very nice. Well, maybe some more questions. Well, I don't see hands, but we had already very good discussion. We had very nice presentation by our professor Revesz, and let me thank you. Thank from all of us. Thanks for a very nice presentation.
Thank you very much for the invitation, and
thank you for agreeing to deliver
the
lecture at our seminar. It was
thank you very much.
really good
My best wishes to all of you.